Good morning everyone. We are with the CH32V003 once more, which is similar to STM, and I believe other manufacturers they have similar layout, but this is the RISC-V variant made by WCH. The chip, also a microcontroller, is still quite complex when we look into the details. Say for example the GPIO support all this configuration with pull-up, open drain, push-pull output, analog input, floating input, can multiplex with other peripherals, and sometimes we can even change the impedance. So why can we change impedance? Is because of high-speed signals, for example. So this is not really so easy when we get first look at it. And therefore we are going to dive into various peripherals of the microcontroller, such as this one, and test out what are the different behaviors when you configure the input with various impedance configuration. And we can see all the peripherals this controller has, and as well we are going to try to dive into the functionality of them through various study cases. I was looking at the GPIO structure. I found out VDD and VDD-FT are different inside the chip, and the FT is due to the 5V tolerant input. And when we see this diagram, we see that the pin is protected by diodes, except that it might be 5V tolerant, so that the VDD-X is VDD-FT, which means that it shouldn't short until above 5V. And we have this complete function diagram of the pin, featuring the pull-up, pull-down resistors, the analog channel, a Schmitt trigger to stabilize the digital signal for digital I/O, the read-write buffers, register, push-pull or open drain. So this GPIO diagram is actually similar in NXP STM range of chip. They use the same philosophy. There is a bit of EMC protection, which are the diodes are here for EMC protection from external voltage. Also an interesting point is when we read the actual input pin. And when we write to the buffer and to the pin via the hardware logic. Although, if for example the pin is shorted to ground and we set 1, we can actually determine this situation by reading 0 from the pin while we have 1 in the output register. And then we have the alternate functions, which are a lot of serial peripherals. So, what's a TTL Schmitt trigger, this chip over here? We can see that it has hysteresis, and how to stabilize the input is that we, going from 0 to 1, we switch, for example, at 1.7V, and switching back from 1 to 0 at 1.4V, say, for example. So we can't really read the input in that regards, but if we read the analog input, we can see that we have the raw value from the pin, actually. So we can even measure this Schmitt trigger if we take care to read in analog value and digital analog, and with some test potentiometer, for example. We can check the behavior of the input and the values used in the physical implementation. That's all for this GPIO. They have described the electrical parameters, and it's all mentioned in the electrical parts of this datasheet. Usually I/Os function as a current source. They have a protection and they limit the current. Microchip PIC usually have for example 20 to 25 milliamps current, constant current source. On this particular chip I don't know, haven't yet listed. And we see that we can program the interrupt, and we have the multiplexing function. Interesting feature is the locking mechanism. That's a safety precaution that makes an input or output pin unable to change configuration at runtime. The equivalent schematic in the input configuration, where we just see the Schmitt trigger and the register, protection diodes, and pull-up, pull-down resistors, optional. They also mention that the EHB clock is used for the I/O port, so the sample rate is the same as this internal clock. When used as an output, we see that the input isn't disabled, so the main function of the pin is an output, but we can read the state of the output to confirm that it is indeed working, not forced to a different state by the external hardware. In analog configuration, the input is disabled via the Schmitt trigger set to off, and the output drivers is also open. We see the software configuration bits and registers. This ADC chapter, they describe the ADC module as a 10-bit 24 meg maximum sampling rate module, which measures from 0 to VDDA. And it's quite complex. We can see from this architecture. It supports mode, automatic scanning, DMA, timed event interruptions, and the configuration can be changed on the fly. Essentially, it is a module inside. I think it has one channels for conversion, and then it links to any of the analog input pins. They just mention a few of the modes over here: single conversion, continuous conversion, automatic scan, intermittent mode, external trigger, double sampling, trigger delay. There is even a watchdog function related to the analog channel. We see the interactions of the pins, and below we have the registers and the explanation how everything is working. So the sampling clock, it seems to come from the EHB bus. We have a power up of the module. It has its own internal power supply. Oh, sorry, there is I believe one conversion module, 10 sampling source, 8 external and 2 internal channels. And by the way, the module can be autonomous since it handles scanning and DMA, so it can write to the memory directly, and the main software, your firmware, can actually read the values from the memory registers directly. We have the calibration signals, calibration registers, programmable sampling time. Data alignment can be changed as well, can be signed, trigger source, conversion mode, and interruption generated after the conversion finished. We have sequences. It's going to scan in this order: continuous conversion, analog watchdog. The analog watchdog is monitoring that the value is above a certain threshold. And we have more configuration bits: the DMA, calibration, continuous mode, sampling registers. So we see that it is a full feature, quite complex, and very flexible, autonomous. The RM manual, reference manual, is for the firmware software, that is the registers, and the datasheet explains the electrical side of the things. And we see here that the I/O are sourcing or sinking 8 mil or 20 milliamps. And if I understand correctly, we have 20 milliamp at 1.3 volt maximum voltage, and VDD minus 1.3 volt minimum voltage. So that's the limitation. So basically at 0 and 3.3 volt, we should be limited to plus 8 milliamp. So it's good enough for driving and for LED. provided we get below this value. We have 45 kilo ohm weak pull-up, pull-down resistors. In some application it's not efficient. Sometimes we need a lower value of pull-up, pull-down, and 5 picofarad of capacitance. And we see that the pins which are 5 volt tolerant, FT, go to 5.5 volts, and minimum voltage this value at the high voltage level. And the standard I/O up to VDD plus 0.3. We have 150 millivolt Schmitt trigger hysteresis, minus 0.3 volt minimum voltage up to this value as a reading as a 0. The limitations on the maximum from the current sink or source from the power pins as well. And we have the maximum frequency 30 meg. So the pins, oh right, we can configure the pin as a 2 meg, 10 meg or 30 meg to avoid reflections, for example on the wires. If we have like a unterminated long wire, we would prefer to use a 2 meg I/O signal, for example. If we have short tracks and we need fast transient, we would use the 30 meg or 10 meg configuration. We have the not reset pin, and it has a weak pull-up, and that's interesting wiring. We don't need to provide an external signal on the pin. Okay, I was going to review the GPIO right now, and I think we will experiment with the firmware and the application hardware in the future. So thanks for watching, and see you sometime if you're interested. And this is the board I'm using at the moment to demo the CH32V003, and I have designed a similar board that I will use in the future for developments. We are looking into the GPIO specification and configuration. We'll continue with experiments and also firmware side of things in the future. If you're interested, you can follow this channel as well. Remember that I design boards and can get into other projects, and some of these projects will be available, for example, on Amazon. And this board actually is a 2-channel CNC driver experiment. Certainly a RISC-V architecture. So if you're interested in this project, you can follow this channel as well. and can get to certainly a RISC-V architecture. So if you're interested in this project, you can follow this channel as well. And this is the board I'm using at the moment to demo the CH32V003, and I have designed a similar board that I will use in the future for developments. We are looking into the GPIO specification. We'll continue with experiments and also firmware side of things in the future. If you're interested, you can follow this channel as well. And can get into other projects, and some of these projects will be available, for example, on Amazon. And this board actually is a 2-channel CNC driver experiment, certainly a RISC-V architecture. So if you're interested in this project, you can follow this channel as well. And this is the board I'm using at the moment to demo the CH32V003, and I have designed a similar board that I will use in the future for developments. We are looking into the GPIO specification. We'll continue with experiments and also firmware side of things in the future. If you're interested, you can follow this channel as well. And can get into other projects, and some of these projects will be available, for example, on Amazon. And this board actually is a 2-channel CNC driver experiment, certainly a RISC-V architecture. So if you're interested in this project, you can follow this channel as well.